Hi, welcome to Physics with Ms. Dalberg. Today we're going to talk about solving acceleration problems with equations. So let's get started. The first thing we need to talk about are the variables we would use in those problems. And so if we look, the first thing you need to remember is that delta x is displacement. And if we talk about x, x represents position. And so if we talk about the final position, it would be represented by either x or x sub f. If we talk about the initial position, it would be x naught. This little zero by the x stands for naught, which is just represents the initial position. xi would be the other way you might see it represented. And so if you subtract the final minus initial, anytime you have a delta for displacement, delta x is final minus initial position. And so displacement is the first variable you'll have to worry about. The next one would be your initial and final velocities. And so final velocity would either be v or vf, and initial velocity is either v naught or vi. The next variable you'll worry about is acceleration, and acceleration is represented by an a. And the last is time, which is represented by a t. So on to the equation. So if we talk about the different variables that you have displacement, initial and final velocity, acceleration, and time. And so you have 5 variables that you're going to find in these equations to solve problems with. So if we look at the first one that you'll find on the formula sheet, the first one is derived from the definition for acceleration. And if we look at acceleration, acceleration is the change in velocity, our final minus initial velocity, over the time. And so if we rearrange this, we could rearrange to find the final velocity and we would get this equation. So that's where this one comes from. This is the first equation you'll find on your equation sheet. The next is one for the displacement. And the next one is the next one you'll find on your equation sheet as well. And so you have initial velocity times time plus 1/2 the acceleration times the time squared. The last equation for constant acceleration you'll find on your equation sheet is final velocity squared equals initial velocity squared plus 2 times the acceleration times delta x. So these 3 equations are ones you'll find on your equation sheet. These are only for constant acceleration. If you recall when we talked about constant velocity problems would use only this equation. Velocity is displacement over time, or rearranging that, you could get displacement equals velocity times time. If the velocity is changing, however, you would need to use an acceleration equation. You could not use this one. And so you have to be aware of what's going on in your problem. I am going to give you one last equation that might be useful, but it's something you will have to remember because it's not on your formula sheet. And the last one is if you find the average velocity, if you take the 2 velocities, the final and the initial, and add them and divide by 2, you get the average velocity times the time to get the displacement. And so in this case, this is similar to this one, except in this constant velocity equation, the velocity is not changing. Here it is. So if you could take the average, you could use essentially the same equation. So how does this work? This is the 5, 4, 3, 2, 1 method. If you know you have 5 variables, and these are our 5 variables, and you have 4 equations, in each of those equations, you have only 3 things that you would know. And so, like, for example, in the first equation, I might know the final velocity, the initial velocity, and the time, and I don't know acceleration. So if I know three things, I can find an equation and use these equations and find the other two, and then I'm one happy physics student. So looking at this, how would I pick which equation I want to use based on what I know and what I don't know? It's easier to maybe look at this and say, well, what if I don't know displacement? Displacement is not part of this equation. This equation will be used when we don't know or care about displacement. The next equation, we know displacement, we know initial velocity, we know time, and we have acceleration. So we could find one of those four if we know the other three. How would you know when to use this equation? The only variable not in this equation is final velocity. So if we don't know the final velocity, and in this case, we wouldn't care about the final velocity either, you would want to use this equation. The next one has final and initial velocity, acceleration, and displacement. It does not have time in it. And so if we don't know time or care about finding time, we might want to use this equation. And the last one has displacement, initial and final velocity, and time. And so the thing that we don't have in this equation is acceleration. So if you have a problem where you're not given acceleration and you don't care about finding acceleration, this might be the one you want to use for that problem. And so let's go ahead and start solving some problems. So we're going to kind of start back from the beginning with our problems, and we're going to do the guess method to find our problem. So the proper way to kind of start a problem is to write down your givens. And this is really important because sometimes you might not know where to start, but if you start by writing the givens, it's enough to prime the pump. So you write what's given in the problem with the units. You write what's your unknown. What are you looking for? Are you trying to find acceleration or final velocity? Write that down with a little question mark after it. Then using the things that you know and the things that you're looking for, figure out which equation to use and write it down. Now, the next step, rearrange that equation to solve for the variable. Many times you'll stop right there, but sometimes you'll want to know the final answer. And so you would substitute in numbers and state the results with units. And so let's go ahead and practice with this. So if we have a runner finishing a 100-meter dash in 8 seconds, determine his average speed. And so the things that stand out to me, 100 meters, 8 seconds, and I'm looking for his average speed. And so my givens are 100 meters, 8 seconds, and I'm looking for, my unknown is speed. Now, I have to figure out what are these two things. So 100 meters, if it has unit like meters, it must be either a displacement or a distance. And in this case, since I'm looking for speed, it's a distance. And then 8 seconds, I have the unit of time, so it must be time. So my equation that I would want to use for this is speed equals distance over time. And it's already rearranged. It's solved for speed, so I can just substitute in the last step my numbers. And so distance is 100 meters. Our time is 8 seconds. And that gives us a speed of 12.5 meters per second. The next one, a test car accelerates from rest at 4 meters per second squared over the course of 200 meters. How fast does the car go at the end of this acceleration? And so if we know our givens, our car accelerates from rest. I'm going to go ahead and underline this 4 meters per second squared. 200 meters, and I have another given that's not a number in this problem, but it's actually a word, from rest. And then for my unknown, I want to know how fast does it go at the end. And so when I see how fast, I know they're talking about a velocity. And I know it could be initial or it could be final velocity. And because it says at the end of this acceleration, we're looking for the final velocity. So our numbers that we know, a car accelerates from rest. The number given here is our initial velocity. If you're accelerating from rest, it means you're initially at a velocity of 0 meters per second. Now the next number, 4 meters per second squared. Due to the wording, I'm not exactly sure what this is, but looking at the units, I have no doubt meters per second squared has to be an acceleration. And then 200 meters must be my displacement. And so my unknown, we said, was final velocity. Now I have to pick my equation. Now the easy way to pick your equation is to look at what are the things you have, what is the thing that you're looking for, what is the thing that you don't care about. I have one more variable that I don't know and I don't even care about. I don't know the time and I don't care about the time. And so going back to this list of equations, if I don't care about the time, I know the final velocity, or I'm looking for the final velocity. I know the initial velocity, I know the acceleration, and I know the displacement. This is the equation I want to use. So I call that one the square ax equation. And if you look at that, I have squares. And I have a delta x. So I have an ax there. So a square ax equation. So now my next step is to solve for final velocity. And I almost have it solved for final velocity. I just have this square there. And so to solve for final velocity, I would take the square root of both sides. Actually, let me do it in this one. Just take the square root of both sides. And final velocity will equal, my initial velocity squared is just 0, and 0 squared is 0. So you can kind of leave that off if you want. I'm writing it just so you know it didn't just disappear. And 2 times my acceleration is 4 meters per second squared. And my displacement is 200 meters. And so if I multiply that, I get 2 times 4 is 8 times 200 is 1600. And that's meters squared over second squared. And if I take the square root, I end up with 40 meters per second. Okay, now I have a car can go from 0 to 30 in 2 seconds. Determine the average acceleration. Okay, so our givens are 0 to 300 meters per second. 0 is my initial velocity. 30 meters per second is my final velocity. So those are 2 of my givens. Two seconds is a time. And I want to find what's the car's acceleration. So the equation that I want to use when I want these 4 things in it is the equation that does not have or care about displacement. That's the only variable I'm missing. So if I go back to this equation page, let's look at these equations. Which one doesn't care about displacement? So if we look at the first one, we have final velocity, we have initial velocity, we have the time. We want to know what's our acceleration. So this is the equation we want to use in that one. And so final equals initial plus acceleration times the time. If we solve that one for acceleration, we end up with final velocity minus initial velocity equals acceleration times the time. Now I want to solve for acceleration, so I would divide both sides by time. And so I end up with a final velocity of 30 meters per second minus an initial velocity of 0 over that 2 seconds. So I get an acceleration of 15 meters per second every second, or meters per second, or I could say 15 meters per second squared. Okay. Now I have another car that can go from 0 to 300 meters per second. So this is my initial velocity. This is my final velocity. I have the units of meters per second, distance over time, in 3 seconds. So this is my time. How far does the car go while it accelerates? So now I don't want to know the acceleration. I want to know how far. So this is a displacement. So my givens are initial and final velocity. And time. My unknown is displacement. So that thing that I don't know, that I don't even care about, is acceleration. And so if we go back to the equations, which equation doesn't care about acceleration? And if we go down here to this last equation, I don't have acceleration in this equation anywhere. I don't care about it. So this is the equation that I want to use. I can find out what's a displacement when I know the final and initial velocity and how long. So going back to that problem, if we say displacement is 1/2 the initial plus the final velocity times the time, it's already solved for the displacement, so we can go ahead and just substitute in our numbers. And so if we do that, our initial velocity is 0, our final velocity was 30, and this time our time was 3 seconds. And so if we multiply that, we have 1/2 times 30, which is 15 times 3. We get a displacement of 45 meters. Okay, the next one, we have an aircraft starts from rest. Starts from rest. I'm going to underline that because that tells me the initial velocity is 0. And accelerates on a straight runway at a rate of 8 meters per second squared. So this tells me my acceleration. How do I know? It has meters per second squared as a unit. See, look at the units for your clue. For 400 meters. And so 400 meters, if this is a distance, this is my displacement. If it's meters, so distance or displacement, anytime you have meters. And I want to know how much time. And so my unknown is going to be the time. I'm going to write down all the things I know. I know the initial velocity is 0. I know the acceleration is 8 meters per second squared. I know delta x is 400 meters. And so if we look at that, the thing we don't know or care about is the final velocity. And so if I go back to look at those equations, which equation does not have or care about final velocity? So if we look at this one, I know the displacement, I know the initial velocity, I know the time, and I know the acceleration. So this equation is the one I want to use. So my equation is delta x equals VIT plus 1/2 AT squared. Now I want to solve for time. And if you look at this, I have time here and here. And so that's like a quadratic equation to solve for time. But if I know the initial velocity is 0, I know this entire term becomes 0. And so I can simplify this to delta x equals 1/2 AT squared. The initial velocity times the time just disappears out of that equation when it's 0. So now it's a little bit easier to solve for the time here. And so my first step, I'm going to multiply both sides by 2 to get rid of the 1/2. And so if I do that, I have 2 delta x equals 1/2 times 2 cancels out and I get 1. And so I have AT squared. The next step, I want t by itself, but before I can take care of the square, I have to get rid of the acceleration. So if I'm multiplying by a, I divide both sides by a to move it to the other side. And it cancels on this one. And so now I have 2 times delta x over a equals t squared. So now my last step, I can take care of the square by taking the square root of both sides. And so now if I take the square root of t squared, I get t. And so I can put 2 times my displacement was, we said 400 meters. And my acceleration divided by 8 meters per second squared. And so now I can solve for the time. And so 2 times 400 gives me 800 on the top. Divided by 8 gives me 100. And if you look at this, this is meters. And then I'm divided by meters per second squared. So the meters cancel and I'm left with seconds squared under that radical. So now when I take the square root, I get 10 seconds for the time. And this last problem. We have the radius of Earth's orbit is 1.5 times 10 to the 11th meters. And I want to know, how fast does the Earth move as it orbits the sun? Okay. And so let's kind of write down what we know. Our givens is the radius of the Earth. So the radius of the Earth is 1.5 times 10 to the 11th meters. And that's maybe all we're given in this problem. We want to know, how fast does the Earth move as it orbits the sun? And so we want to know what is our unknown. I'm going to go ahead and write this here. Our unknown is the speed of the Earth. What's the speed of the Earth when we know the radius of the Earth is 1.5 times 10 to the 11th? Now, if we think about that, here's the sun. So here's the sun, and here's the Earth, and the Earth orbits the sun. And we're given this radius here, and I want to know, like, how fast does it move? So the Earth is moving in this orbit. How could we find that out? And so what are the things we would need to know? So to find the speed, the equation we want to use is distance divided by time. And I'm not given distance and I'm not given time in this problem. but some things are implied. For example, if I want a distance for something moving in a circle, I know the distance equals the circumference. And how would I find the circumference of this circle? And so if I know 2 pi r is a circumference, I'm given the radius, I know pi, I can easily find the distance the Earth travels. And so 2 pi times 1.5 times 10 to the 11th meters is the distance. And this is 9.4 times 10 to the 11th. Okay. And so that's the distance. How do I know the time? So I still need the time. Well, I know it takes a year for the Earth to go around the sun, or it takes 365 days. So 365 days equates to what? If I want to do it in, I don't know, maybe hours or minutes or seconds, I will do meters per second to just kind of compare to some of the numbers we're going to use all year. So if I know in every one day, there are 24 hours, and I move this over a little bit, give myself a little more room to work. Okay. And I know for every 1 hour, there are 60 minutes. And I know for every 1 minute, there are 60 seconds. I have converted days to seconds. So days cancel, hours cancel, minutes cancel, and I'm left with seconds. And so if I multiply this, I get a pretty big number. I get 31,536,000 seconds. And so if I take this really big number divided by this really big number, I get 9.4 times 10 to the 11th divided by 536,000, and that will be meters per second. So and if we round to significant figures, we get 3.0 times 10 to the 4th meters per second. So the Earth is moving pretty quickly around the sun. Okay. And we'll stop there.